Hi, thanks for coming. So the talk is on exact decoding, and this is a joint work with Marc and Lucia. So in SMT, we typically talk about Viterbi decoding, and by that, I mean that there is a certain input, there is a space of derivations which is compatible with this input. It's defined by your model. Here's a phrase-based model, and we're interested in finding the best among these derivations, the best under a linear model. And this linear model, it typically decomposed into some local features, those for which we have a very strong independence assumption, and they assess steps of the derivation independently. And some of those are not local. They have either weak assumptions or they have no independence assumptions at all. An example is the language model, which requires the yield of a derivation, so the actual string that the derivation produces. And that notation over there means this set of derivations weighted by that function. So this weighted set can be seen graphically as a hypergraph. And this hypergraph is the result of the intersection of other two objects. One, the translational hypergraph that can be locally parameterized, so you can have all your local features in there. And you have a target language model, which you can see as a finite state automaton, and that will take into account the non-local feature. And then in phrase-based MT, with a distortion limit and an n-gram language model, forgetting a few other constants that should appear over there, you get this order of magnitude for these objects. And I over there is the length of the sentence, the input sentence, D, the distortion limit, delta being the target vocabulary, which is usually linear with the input, and you have there the exponential dependency on the n-gram order, the order of the n-gram language model. And the problem is that this intersection is too large. So everybody here is probably familiar with the fact that we can't do exhaustive search here. It's too hard for dynamic programming. So the idea just to set a difference with previous work. In previous work, typically people relied on compact models or even toy models. And the farthest I saw was exact decoding with 3-gram language models. So here we have large models and we go up to a 5-gram language model. To get the intuition on how we're going to go about solving this problem is, that's the automaton that represents the complete n-gram language model. And another way of seeing it is imagining that there is one simple automaton for each n-gram that you have in your vocabulary, in your language model. And if you reduce them through intersection, you would get back to the full big automaton. So the idea here is that we assume that not every n-gram participates in a high-scoring derivation. And the problem is then which ones do and at which level of refinement. So the strategy is to start with very strong independence assumptions from a very simple language model and revisit those assumptions as necessary. And I have an illustration of how this goes with this algorithm based on OS star. So these are the solutions for some input. And this is the F, the target function parameterized with the high order language model, which we can't really afford to represent, so I'm showing with circles. I can only show you because the support is very small here. And then we upper bound this by a simpler function G. That one is simple enough so we can represent it exactly. We can compactly represent it into a hypergraph. And the idea is that we're looking for that one over there, this start, the derivation, so the argmax, but we can't afford searching through F. What we can do is find G's argmax. And once you have the derivation, the argmax of G, you can actually assess it with respect to F. And if you were to stop the search right now, that's the best we can tell about F. This is the solution. It's likely to be a poor one. And how we know it's good or bad? Well, we have a bound on the error because we know that the actual solution must lie within that interval because G is an upper bound to F. What we can do here is, well, we're not satisfied with this error that we have so far, and we refine G so that G looks more like F, at least around that derivation. And a very simple way of doing that is imposing that for that specific derivation, G actually assigns the F score. And if we repeat, and this comes at a little cost in complexity because you just add as many nodes to the hypergraph as there are nodes in the derivation, at least for the simple operation. We're going to talk about some other operations later. And if we repeat the strategy, we find a new argmax for G, then we can assess its F score. Then we have a new estimate on the error. And you see that the error bound, it goes smaller now. It's smaller because G can only go down, and G remains an upper bound, and our guess for the best thus far can only go up. And then, if we're not yet convinced, we just iterate. So basically, I found a new argmax, I assessed, I found a new error bar, I'm not happy with it, I'm going to refine it, find a new argmax. We are pretty close to proving we have a small error over there. We actually happen to find the best derivation, but we're not convinced yet. We cannot prove, we don't have a certificate. So we continue. Refine, find another, and the next argmax, the error is very small. We could even stop now maybe, but we want to go for a 0 error. And also we refine the previous one, we finally find the argmax with a certificate. And that's basically, that's the intuition of the algorithm. And in an algorithm, it's pretty simple, so let's call that epsilon our tolerance. So how far you accept to be from the optimum. And let's set that to 0, for instance. Then what you do is once you have your upper bound, you maximize, you assess it with respect to f, and for as long as the error is not small enough, you iterate, and you collect from the argmax some evidence of over-realistic estimation. So basically, you are being too optimistic. And based on that evidence, you refine G. And then you find its new argmax, update the error bound, and continue. And when this falls to 0, basically, you have the optimum. So we there have a proposal, and we have refinement action. So let's talk about these two. In the proposal G, basically, we replace the true language model distribution, PLM, by an upper bound, QLM. And the key to make it feasible to represent the proposal exactly is to make strong independence assumptions regarding Q. Basically, if you have a substring alpha, black cat, substring of y, the black cat over there, alpha's contribution to the true language model score is the one shown over there. So basically, the true language model distribution has access to the complete history. We are just going to change that story for Q. So Q only has access to the history within alpha. It doesn't have any access to words outside alpha. So you see there an abbreviated history. And the key to make it work is here in the bottom, is to make Q, the distribution over n-grams, be an upper bound on the distribution on the true distribution over n-grams. Let's check what this is. So basically, we want to score an n-gram in its most optimistic context. We're going to maximize away the history. History being any sequence of any string in the vocabulary H over there. Well, that's any string in the vocabulary, so that cannot be efficient. But because our n-gram language models, they are actually back off, they back off to shorter prefixes, and that's how we define the entire distribution over arbitrary n-grams, it turns out we can efficiently compute that quantity, pre-compute that distribution by storing this, what we call a max ARPA table. You start from an ARPA table where you have the known n-grams and the conditional on the n-gram and its back-off weight, and you basically find an optimistic view of the last two columns. In the paper, you have the algorithm and the proof for that. And if you have that, then this simple expression here is actually an upper bound on the language on the n-gram conditional probability. And once you have that, then the proposal G is actually a standard hypergraph, one of those that we use in normal cube pruning and beam search. And nothing changed except for one thing. It does not store language model state. So there is no language model information that is preserved, which means that if this was the complexity to represent the actual function, this is the upper bound. We literally cancel the dependency on the order of the language model, the exponential dependency, the part that is very expensive. Well, that can't be done for free. There's a consequence. Eventually, you have to start refining this function, and refining means breaking these independence assumptions that we introduced, meaning composing smaller n-grams into larger n-grams, literally bringing G lower, closer to F. And two examples. One is the one in the illustration. You simply say, okay, for the new G, we're going to have exactly the same as before, except for its argmax, for which we're going to have the F score. That's very local. We are basically dealing with one derivation at a time. That might be very inefficient. A different way is saying, well, let's correct all the derivations. Let's look for occurrences of a certain n-gram, HPZ, count how many times this happens in the yield of the derivation, and let's re-rate such that Z, which used to be conditioned on P, now it's conditioned on HP. So basically, you are breaking an independence assumption. You are introducing a word in the context of PZ. And for a bigram, that would be an automaton that incorporates this kind of refinement, and you can do that via intersecting the hypergraph with that automaton. And you can generalize that for bigrams, trigrams, and so on. The problem here is that this is too global. You refine derivations that already score very poorly. We need a compromise solution. A compromise solution comes from language model state refinement. So again, we're going to break independence assumptions, make large n-grams, but we are not going to do that everywhere in every derivation. We're going to focus on the derivations that we know are high scoring. Suppose this is the argmax. Their x, 1, 2, and 3 are nodes in the hypergraph. And at this point, X3 doesn't store any language model information. So we know for sure that black has been scored completely independently from D. And what we are going to do is we're going to refine X3 into a new node, X3 prime, which memorizes the context D. That way, we basically, well, in terms of the operation, it split the incoming edge to X3 on the basis of its span. If it ends in D, it goes to the new node. And for the outgoing edges from X3 prime, they are reweighted copies of the original one in which we get the chance to condition on D having occurred. And this is actually more involved. It's connected to a local intersection of that kind. But you can see that that's not a regular expression. You see there is a node there. That's a kind of a recursive expression. So that's too involved to be computed. And this language model state refinement is going pretty close to that, but it's still remaining in an efficient setting. And then as for the refinement actions, what we want to do is we would like to get a new G such that its maximum is as small as possible. Because if we could refine that in one go, we would basically get to the F's maximum. As we can't do that, we design strategies. And these strategies, they are heuristic in the sense that it's arbitrary. You could choose whatever you want. But the search is not heuristic here. So, yeah. One such a strategy, the one we use, is refine all the nodes that participate in the argmax and refine them by adding one word to its right language model state, and just one at a time. So in an illustration, suppose that this is the argmax derivation. Now I've bracketed them. I'm sure it's not very clear to see from this distance. Maybe it was unfortunate to be in a vertical setting, but I've numbered the brackets so that you have an idea of the nodes in the hypergraph. And if this is the maximum, we could basically go bottom up, so starting from X2, and continue refine spans that continue from X2 by conditioning on D. And this means that black given D would be reweighted over there, and you see the yellow bars are showing some gain, some refinement, bringing G closer to F. We can do the same bottom up, so X6 by conditioning on black, and then basically you get cat given black, and other words given black. And you get some other points there that have been lowered a bit more. And you can do it again. So basically the end of the sentence given cat. And I'm going to clean up a bit and just show the final distribution. That is it. And you will see the difference here is that we don't get to lower the error just in this derivation. We actually do it in a few more. But at the same time, it's not global. It's not everywhere in the graph. So as for the experiments, we do German-English translation using WMT datasets. We use the Europrol for phrase extraction, maximum phrase length and maximum translation options compatible with what people do in the task, in the shared task. And we train unpruned language models with 25 million sentences of different domains, language model interpolation and tuning using the test set 2010, Batch-Meyer tuning with for the tuning we use the cube pruning with a large beam, and then we decode all the 3003 sentences using our approach. And distortion limit D equals 4. So we have here different language model orders, and time to compute the initial proposal, which is not a function of the order of the language model, because as I showed, there's no dependency. We overlook the language model in the moment of the creation of the initial proposal. And then that's decoding time, on average, number of iterations, and the size of the hypergraph in thousands of nodes and edges. We see that time and iterations, they go exponentially with the order of the language model, which is expected from the perspective of the complexity, which is not so good for whoever wants to use it, because, well, when you go for cube pruning and BIM search, you are really looking into having into having more control on that. Basically, we're losing here control on the worst case complexity. Good news is that the size of the hypergraph is 3 orders of magnitude smaller than what you would get with a beam search when beam search using beam search with a beam of 1,000, in which case you would be close to decoding exactly, as the results we'll show later. And this is comparable, and in some cases, especially for the 5-gram language model, just a little bit bigger than what you would have with cube pruning. And by little bit, I mean about 15%. Let's have a look at the search errors made by cube pruning. So cube pruning makes search errors like that. Here is the beam parameter. It's nice to get confirmation that as you go an order up with the beam, you go an order down with the errors. And it's also interesting to see that with beams of 10,000, in a 5-gram language model, cube pruning is performing basically exactly. Although we don't have a proof, the error is unbounded, we know empirically that it's very close to the optimum. And beyond 100, you see that, well, from 100 to 1,000, you see that that's, oh no, it's an next slide. Here, let's have a look at the blue scores that you get for that. So it's also nice to see that with less search errors, you do get a better blue score. And here, in the last row, you see what you get with exact decoding, and over there, what you get from cube pruning with different levels of pruning for different language model orders. And let's have a look over there. From the 100 to 1,000 in the last column, you see that from 20.69 to 20.29, 21.9, you have more than a blue point there. And I've seen a few papers in this conference reporting beams of order 30, 10 to 30, 10 to 50, I've seen. And I wonder why, because the jump from 100 or 1,000 is not that bad in terms of speed for cube pruning. So yeah, and it does hold a lot of search errors in there. And for conclusions, we've presented a strategy for exact decoding that performs in manageable time. It only explores a fraction of the search space. We have search error curves for beam search and cube pruning. Beam search is not here on the talk, but basically beam search is performing exactly at about 1,000, for a beam of a size 1,000, but it consumes a lot of memory. We've done that with large phrase tables and large 5-gram language models. And in our case, exactness comes at the cost of losing worst case complexity. So our worst case scenario is the full intersection, in theory, but in practice, we demonstrated that the algorithm is practicable. Some recent developments that I don't have time to talk right now, but if you're interested, you can come to me, is exact k-best and exact sampling, which is, in my opinion, the most interesting thing you can get out of this method. As for optimization, there are a few things we can do. We can early stop the search on the basis of the error bound, and that might be interesting, might lead to good blue scores, because for most of the derivations we have there, we find the best translation as early, we find the best translation very early, but the score remains unchanged for the last 60% of the search, of the iteration. So we are pretty convinced that we found it quite early in the search, but we need to lower the error to 0 before we have a certificate. So if you are willing to lose the certificate, we can get very good speed ups. I have to quantify the impact on blue. And as for pruning, in optimization, you could do some error-safe pruning on the basis of this error bound. The reason why I'm not exploring that is because I'm quite interested in sampling, and there I really don't want to prune the distribution. And as for speed ups, there are a bunch of things we can do, actually. We can be more selective with refinements. The strategy was to refine every node participating in the argmax. Well, that's probably that's actually a very naive strategy. There must be only a few n-grams that are actually responsible for that derivation showing up as argmax in the upper bound. We can use Lagrange relaxation to deal with the power set constraints in phrase-based MT, and that would allow for a higher distortion limit without really having to pay the price of having a much bigger automaton to start graph to start with. And we can also do more grouping. This is based on Ken's work. So comparing to his work, we are also doing grouping at the level of nodes, but we could also do grouping at the level of edges, and that could make a much more compact hypergraph, which then leads to quicker iterations. Not fewer iterations, but quicker ones. And it's straightforward to generalize this to higher models. And I'll happily take questions. Thank you.
Time for questions.
So in your refinements, you say that you're refining all possible n-grams, right? So in the particular derivation, like, what does that exactly correspond to? I just didn't.
What? Sorry, in the particular derivation?
So when you say as you refine the scores for all the n-grams, you mentioned in the conclusions and in the slide that you do reduce the scores for all possible n-grams. Corresponding to that particular derivation?
Yes,
could you
corresponding
elaborate?
to so I correct the n-grams that are spanned by strings under a certain node. So the node being the node that participates in the derivation. So say here, say I could correct every bigram that starts with D. So say I want to correct D black. But I want to generalize a bit. So I also want to correct the dark, the cat, the feline. If I simply use a finite state automata for that and intersect a hypergraph, that will have the impact of refining every derivation. And many of them already score poorly enough. So I don't want to do that. Instead, we want to condition on x2. So we want to correct continuations of x2 such that this continuation is such that a string under S2 ends in D. You see?
I see.
Yeah, it's a little bit more restricted.
Thank you.
No problem. Thank you.
So one question, you were talking about worst case or loss of worst case guarantees, but empirically you didn't seem to run into that. To what extent do you think that is specific maybe to the language pair or the data set? I mean, what do you anticipate could actually be a problem for that worst case?
Right. I don't think it's very dependent on the language pair, although when I did some experiments with French, I could go a bit farther with the distortion limit, so then there would be a dependence on language pair. But the dependence that comes has to do with the number of reorderings that the model likes. Right. So the more reordering the model likes to do, well, the less the model care about long jumps, the more important it becomes, the more it cares, the more important the language model becomes. And then when you go and upper bound the language model, it's like saying that most of these bars go very high. Yeah. And if you imagine that all the bars go higher than the star, if all of them went higher than above the star, I would have to refine every single derivation. Eventually, I would have to do at least one refinement to every single derivation in this plot. So in this sense, there is a dependency, see, which it has to do with the distortion cost. I still think that it's not too bad. It's not a crazy assumption to say that not every n-gram must be intersected everywhere in the hypergraph. The question that remains is really how do you trade off between a local refinement and generalization power? So you want to do fewer refinements. So that's the question that remains there. And to deal with the distortion limit, I think the best direction is probably to try and incorporate some of them via Lagrangian multipliers just to avoid the automaton, the hypergraph growing too large from the beginning. Because if it grows too large from the beginning, it just means that every iteration is slower, even though you continue exploring the same amount of the same number of nodes.
Right.
Yes.
So exact decoding is fun, maybe a bit excessive. So typically there's a trade-off between speed and quality. Mm-hmm. So have you compared that for your decoding method? I mean, you can stop any time. You don't have to go all the way to the end. Yeah. For your method compared to beam search?
Right, so you would like to see, say, a plot with the different tolerance on the error and the blue score, right? I don't have that plot. I don't have that plot, but I've been requested that already this week, so I think I'll add that table to the paper on my page, but I don't have that plot. My feeling is that there won't really be a big drop, at least in this 40% range that I told you. So, like I said, the score remains unchanged for the last 60% of the search. So I think you can really play with the epsilon parameter and have a much faster decoder with this error-bound guarantee. And yeah. Mm-hmm.
Thank you for a very interesting talk.
Thank you.